It says I'm live, so I must be. I found a way on Blackboard to load following information. So as soon as everything is closed up for you on Tuesday, Blackboard will automatically open the new video. It'll automatically open the new video guide. I'm not sure. I'm going to work with the MyLab Math and see if I can get those to open up right at the end of class as well. I'm imagining I probably can, so that way I don't have to think about it. I tend to work long on Tuesdays with the two classes that you folks have, and then I have another basic algebra class right after this one. And usually I'm done with that about 7:10, and then sometimes I don't necessarily remember where I left the loose ends. So this is going to be really helpful. So I have the video ready to go, the video guide ready to go, and they won't appear. And in the past, I put those up in advance, and the problem is that students click on the wrong video and the wrong video guide, so they're sometimes a day ahead. So this will work great as soon as your class ends, either the 2:15 class or the 3:45 class. As soon as those classes end, as soon as your class ends, video will appear on Blackboard, video guide will appear on Blackboard. MyLab Math will appear on the MyLab place where it should. Gosh, I guess that's everything. The only thing I'll have left to do before Wednesday will be to put the finishing touches on the next day's activities. I have had to adjust those a little bit because we didn't get the opportunity to cover integration by substitution, and so I have to sort of juggle things around a little bit or offer a little explanation. It hasn't been a lot of work, and neither have the videos. So with that said, we have the video guide out for today. We have the last video that's going to be due tomorrow. I think that's, I'm sorry, the last activity. I think that's activity 19. I've uploaded activity 20, at least that's to my best of my recollection, the one that we're going to cover tomorrow. Yeah, I did. I did that. I uploaded that yesterday. So if any of you have any questions over any of those things, I'm going to make sure I have them all open on my computer screen now. So throw your questions in the comment box. And I'm guessing most of my questions are either going to come from the activities that are we'll talk about in class tomorrow, the activity that's due before class tomorrow, or the video guide. So I'm going to make sure that I have at least those two activities open. Yeah, so I guess those are 19 and 20. So 19 is due, and 20 is the one we're doing in class tomorrow, in case anyone wanted to get a head start on that. We will have a quiz at the end of each class from here on out, except for on test days or days right after the test. And that's outlined on the little calendar that I've loaded the first thing when you open up the Blackboard page. Activity 19, how do we start activity 19, question 2? Well, hopefully you had a decent chance to read that little paragraph ahead, and you should realize that on the graph down here, this is the power, and this is measured in, was it kilowatts or megawatts? I forgot. Kilowatts. And this is the hours since the shift started in this time. Okay, so we have units to units. Each rectangle will account for how much energy. Well, if you look at a rectangle on here and you measure this out, see that's 10,000 at the very top. So this is 10,000 kilowatts tall and 1 hour wide. So if you take that area, 100 kilowatts times 1 hour, and the amount of energy that's contained in one of those blocks is 1,000, and you're going to multiply these units together, kilowatts, and since they're multiplied, we'll put a dash there, kilowatt hours. So each of those little boxes is 1,000 kilowatt hours. Getting those so correct is really important. It's always the units on this axis multiplied by the units on that axis. That never changes. And that's been one of those ideas that's been a little more difficult for students to grasp. So I'm spending a lot of extra time on it this semester in the videos and in these video review sessions as well. Looks like I jumped from part A to part C. Did I really do that? Well, I checked activity 20 several times yesterday, and it looked like I had that one right. Estimate the required energy for the 5 to 10 hour period. Okay, so if you look over from 5 to 10, there's 5, there's 10. And what you could do to estimate that is count up how many of those boxes you have, and multiply that then by 1,000 kilowatt hours. Each of those boxes is 1,000 kilowatt hours, represents 1,000 kilowatt hours of energy. So if you would just count all those up, and some of them are partial blocks, whatever, that's one way of getting it. The other way would be to set a line across here between 5 and 10 that sort of balances out the dips and the valleys and the peaks of this one. So you could also sort of draw a nice horizontal line across here that sort of evens out the overages there and the underages there. And I'll show you how I would do it so that I was fairly certain. In fact, to me, this is the easiest way to do it. So there's a nice horizontal line, and you have the horizontal line in the correct place if the area where the function is over your horizontal line, I'm going to cross that up, left, down, right. If that area there is equal to the area that I'm cross-hatching the other direction, if those two areas are equal to each other, then you have this average power right where it should be. So another way of doing it then is sort of replacing this whole area under this curve with just this area of that rectangle. They have the same area. An area of a rectangle is easy to calculate out. So area would equal base, which is 5 times height. And if I look across that, I would estimate the average height to be 10,9,876. Oh gosh, I don't know, somewhere around 6,000 kilowatts. So I think that would work as an estimate. Multiply 5 hours times 6,000 kilowatts, that'd be 30,000 kilowatt hours. So that'd be a good way to start those. I hope that helps. Here. Can you show how we do number 3B? Sure, I will take a look at 3B. I think I didn't, neither of my classes had questions on problems. No video there whatsoever. 3B is a definite integral. Since it's a definite integral, we're going to get a number. Definite integrals are numbers. So we're looking for, and by the way, I'm going to draw a quick graph. It's x squared plus x minus 1. I think the graph looks something like that. And we're going from -8, you know where that is, -2. It's got to look something like that. I'm looking for that area of the curve. -8, -2, x squared plus x plus 1 dx. There's really just a couple of steps for finding the definite integral, the area. That'll give us the area under the curve there. Take the antiderivative, 1/3 x cubed plus 1/2 x squared plus x. Again, I raise the power, for each of these terms, I raise the power by 1 and multiply by the reciprocal of the new power, so I was consistent on that. I'm going to find my picture back so I can see if I'm stepping out of screen or not. There we go. Okay. Raise the power by 1, reciprocal of the new power, and this one raise the power by 1, I guess. I don't have to put the plus c in here because I'm going to evaluate this between x equal, gosh, I want the bigger number here. This is -2. Evaluate that between x is -2, Now would include a plus c, and then we're going to subtract off this evaluated at x equal to minus 8. And that would amount to, if I had the c at the end, I'd end up subtracting that anyway. So the plus c and the minus c would cancel. So let's see if I can do this arithmetically. Minus 2 cubed is minus 8. So this is negative 8/3 plus, if I plug a minus 2 in here, I get a 4. 4 times 2 is 2. Minus 2, I guess I get a negative 8/3 for the top. Okay. Now we'll do the bottom. Plug in a negative 8. 8 times 8 is 64. 64 times 8 is, let's see, 32, 512. So that'd be negative 512 over 3 plus, see, 8 squared is 64. 64 divided by 2 would be plus 32. And then plug the negative 8 in there, minus 8. So let's see if I can make this make some sense here. That's going to be 24 minus 512 over 3. So I'm going to take this upper one and subtract then this from it. So it'd be negative 8/3 plus 512/3 minus 24. And I'm doing this in sort of a strange manner. I'm hoping that this is going to be a nice round number when I'm done. Minus 8 plus 512 is 504. Oh, look at that. Over 3 minus 24. 3 divides into 504, goes in there 168 times. Minus 24, looks like that's 144 if my calculations were correct. You have a little bit of an advantage here. You have a calculator at your ready that allows you to do the adds and the subtracts there with a little less, fancy arithmetic math than your instructor was able to do. When you grow up in the era before calculators, you learn all sorts of fancy little things to eliminate as much hand-wringing math as you can. So that's what I got. I got 144. I think that's right. I didn't really have a chance to make a answer key on this one, or at least I didn't bring it with me. I have an old one from previous semesters. Maybe I should just look at it. But if any of you got anything differently than this, let me know. This came out to be negative, what, 2.67 about? I don't know what that is, but it's definitely negative. So you have this negative 8/3 minus this way bigger negative, switch the sign around and add. I guess it's 144. Okay, you're welcome. So I'm ready. What other questions do you have, either looking slightly forward or looking more forward? And hey, if you got something from before, looking backward, I don't care. Yay, 144 it is. Good. And on a problem like this, I mean, if I were you, I'd work it all by hand, and then I'd bring up Wolfram Alpha. To me, it's the friendliest and least expensive math help thing. I guess there's other things as well. There's differential integral calculators as well, but I go Wolfram Alpha. .com, and you can say, you can type in, it'll ask you what you want. So you tell it you're going to do a definite integral, it'll say what's the function, what's the upper limit, what's the lower limit, what's the variable. And that way you can check your work on these things. I think there's other, I think if you pay a little bit to Wolfram, it'll go step by step by step. I think there are other websites that'll go step by step by step as well. That way, if you do make a mistake, you can catch it. But to me, this is the handiest way to do one of these if you want to just check your answer. And hey, we have those tools. Let's make use of them, huh? I think one of the things we're tending to do in this class is move a little bit away from a lot of the long calculation problems and move more into the applications. And you'll see, like on tomorrow's quiz, it's an application question. 1, D, E, and F, sure. Let's see what we got here. 1D. Terminal velocity is the top speed that it can reach observing the graph. Yeah, well, if you look at the speed here, you can tell the speed is increasing, but then it starts increasing at a slower and slower rate. It's just about peaking out here. So if you could put an asymptote around there that it looks like it's getting closer and closer, the longer that parachute is falling before she pulls the ripcord and opens the parachute, there's going to be a limiting factor about how fast she can descend, and that limiting factor is where the force of the wind that's holding her up is equal to the force of gravity pulling her down. So there's no need to there's no way she can accelerate further. So if you just sort of look at this graph and figure out where it's going to go, somewhere around 185. Now, what I could do if I wanted to make sure that that was true is I could take the limit as x approached infinity of the function, which is 185 minus 185 e to the negative, I think it was 0.173t if memory serves. I'm gonna double check that, I guess. Yep, I did that. So you could consider what happens as whoops, t is a variable, as t goes to infinity, and this is the function, by the way, since that's a negative exponent, I can put it there in the bottom. And then observe what happens. As t gets bigger and bigger, e to a function gets huge. That's exponential growth. You've heard about exponential growth, right? There's exponential growth. So we have a 185 divided by a huge number. That's going to make that get closer and closer to 0. So using a limit, I can absolutely ascertain that that's 185 feet per second. So that's part D. Now E and F take us back. I guess this took us back to the first exam. D and E take us back to the last exam. What can we say about the first derivative on the interval from 0 to 40? And that's all I drew here on the graph was interval 0 to 40, because who knows, maybe after 40 seconds you pulled the ripcord. So what can we say about v prime of t in this interval from 0 to 40? Well, the first derivative tells us whether the function is increasing or decreasing. The function is increasing, and since the function is increasing, what does that tell us about this number? The second derivative tells us information about how the slope is changing, whether it's concave up or concave down. So what do we know about the second derivative in between 0 and 40 based on the shape of the graph? That's what our second derivative, that's information our second derivative gives us. And our first derivative gives us information about whether the function is increasing or decreasing. So with those two things said, what do I know? What type of value must the first derivative be, all for any number between 0 and 40? And what type of value must the second derivative be, just based on the shape of the graph, for any number in between 0 and 40? Put your answers in the chat, and we'll see if anyone is able to get that figured out. Again, it's just what we did on the last exam. Sort of questions like this, I think, were on the multiple choice section. And by the way, tomorrow's, yeah, I mentioned that. Yeah, tomorrow's quiz will require the equation editor again, so hopefully everyone has all that figured out. And by the way, I did answer, yeah, I think I did, yeah, I did problems 1 and 2 in their entirety during the 3:45 class on Thursday. And I've bookmarked the time, so if there's other sections that you're not precisely clear on, make sure you're precisely clear on them. I think we as a class worked every single part of problems 1 and 2, and I've timestamped those on the video. That's in the that I uploaded to Blackboard. Yeah, the first derivative isn't increasing though. The function is increasing. There's no doubt the function is increasing. And if the function is increasing, what does that tell us about the value of the derivative? The first derivative does tell us whether a function is increasing or not. That much is correct. What sort of number must this derivative be if the function is increasing? By the way, the first derivative isn't increasing. First derivative is actually decreasing. First derivative gives us the slope. Here the slope is really steep. Here maybe the slope is 1. Here the slope is a half. Here the slope is a third. Here the slope is a quarter. The slope is decreasing. So to say that that first derivative is increasing would be incorrect. First derivative is not increasing. Here's a graph where the first derivative is increasing. Here the slope is -8, here the slope is -6, here the slope is -2, here the slope is -1/2, here the slope is 0, here the slope is 1, here the slope is 2, here the slope is 7. So as we read across this one, which is a graph which is concave up, there's one where the slope is increasing. The first derivative is increasing. But here the function is increasing, so what do we know about the value of that first derivative? Okay. Well, the function is increasing. So if I have the first derivative, say, of x and it's equal to 3, that tells me that the slope is 3. What does the slope of 3 look like? It's going up like that. If I have v prime of x is equal to 1, that tells me that the slope is 1. If I have v prime of x equal to 0, which is what we've looked at so many times on this on that last exam, that tells me the slope is 0. Here the slope is, maybe here the slope is -1, so the first derivative would be -1. In this case, the function is always increasing. Increasing means a positive slope, so this is positive. Why? Because the function is increasing. The second part, what sort of shape do we have? We have a shape which is what? Concave up or concave down? For the whole interval from 0 to 40. And if this is either, call it either concave up or concave down, once you've determined which it is, what does that tell us about the value of the second derivative? It's definitely concave down. And since it's concave down, what value must the second derivative take on for every point between 0 and 40? Choices are positive, negative, or 0. So what value must the first or the second derivative be? Positive, negative, or 0 in between 0 and 40? There you go. So what else do you have for me? Yeah, could be. Speaking of the exam, I have a student that's still to take it, supposed to take it on Friday, and I think I set one of the timers wrong. It's like 2 timers. I have to set when it's available and when it's completion date, and I think I messed up one of those. So still waiting for that last student to take the exam. If I were to draw some graphs, we will cover everything. If I were to break these down into little sub-regions, on this part over here, here the first derivative would be less than 0 because it's decreasing, and the second derivative would be bigger than 0 because it's concave up. Over here, the first derivative would be bigger than 0 because the function is increasing. The second derivative would also be bigger than 0 because it's concave up. On this part of the graph, the first derivative would be bigger than 0 because it's increasing. The second derivative would be less than 0 because it's concave down. On this area of the graph, the first derivative would be less than 0 because it's decreasing. Let me get this more toward the center. There we go. And the second derivative would also be less than 0 because it's concave down. On this part, the first derivative of x would be less than 0 because it's a decreasing function. And the second derivative of x would equal 0 because it's not concave up, nor is it concave down. There's no curvature at all. On that little bit right there, the first derivative of x would be bigger than 0 because it's increasing. The second derivative of x would be equal to 0 because it's not concave up, nor is it concave down. I think there's really just one other case to look at. Well, I could look at these points. At that point right there, the first derivative of x would actually equal to 0, and the second derivative of x would still be bigger than 0. At that point right there, the first derivative of x would equal 0, and the second derivative of x would be less than 0. And these were the 2 parts that were necessary for the second derivative rule. There's where we have a relative max, and here's where we have a relative min. In both cases, we have a critical point. We have a first derivative equal to 0. If the graph is concave up, it's a min. If it's concave down, it's a relative max. Yeah, we'll see the right answers on exam 3 as soon as my last student finally gets to it. So really that takes care of all I think every single possibility. Oh, no, there's one more. So hopefully you have the first part of this copied down or rerun the video if you want. I guess there is one other case, and that's where you have a constant function. So there's the function right there. The first derivative is equal to 0, and the second derivative is equal to 0. That function is not increasing nor decreasing. That function is not concave up, nor is it concave down. So that really settles everything in place as far as all the different possibilities, combinations of first derivatives, positive, negative. Any other questions on anything in particular or in general? I still have a good half hour in my window of availability here, and I'm more than happy to spend it with on anything you might have. Yeah. And you'll have a chance to do these because I know there are 3 or 4 questions on the final that really look at this closely. And as I look back on the last exam, the multiple choice questions were done fairly well, and that's where I asked these. And that's an unusual happenstance. Usually multiple choice questions are done less well than long answer ones. Anyone else have anything for me? So we've had a chance to start on tomorrow's stuff. Just a couple of applications. We already did a couple of applications on this activity. I'm going to sort of pound home the idea of what each of those blocks underneath the curve stands for as far as the units are concerned, what those blocks of area stand for. And once you have that down, the conceptual questions on the exam should go fairly quickly and fairly smoothly, but until you get those down, then it's a bit of a struggle. Any questions at all? And the difference, I guess, this time and the last several semesters is usually at this point after we did the area under the curve, we had the next exam, but it didn't seem to make sense to do it this time. I've included a couple area between the curves, and that moved our exam back where it should have been, like the week before finals week. Okay. Okay, sun's out. I'm going to go spend a minute or two outside. Good chatting with you all today, and I'll look forward to seeing you all in class tomorrow.